We've been looking at statistical significance, and to this point we have assumed that the dependent variable that we're analyzing is interval level dependent variable. We can use the 95% CI, we can calculate p-values and get very precise estimates of how often we would observe the pattern that we're seeing under the assumption that the null hypothesis is correct. But what if we don't have an interval level dependent variable? What if we're doing cross-tabulation analysis and we have nominal or ordinal level variables in the table? That's where the chi-square test comes in. The chi-square test is perhaps the most commonly used statistical test in cross-tabulation analysis. It's one of the oldest tests of significance still in existence or still in use. The chi-square test determines whether the observed dispersal of cases depart significantly from what we would expect to find if the null hypothesis were correct. So in this way, the logic of hypothesis testing is the same as before. The null hypothesis is here. The null hypothesis has an expectation about what the data can be expected to look like. And then we compare our observed cases, our observed dispersal of cases with what the null hypothesis expects us to find. Let's look at a crosstab here. This tests the hypothesis that men and women will have different views of diplomacy versus military force. We have 530 females here, 511 males, and if you're just without any knowledge of chi-square, if you're looking at this table, you would say, well, let's see, about 46.2% of females favor diplomacy versus force, compared with 34.4% of males. So, there's over a 10-point drop, about a 12, almost a 12 percentage point drop in the preference for diplomacy across genders. So we would be tempted or inclined to say that our hypothesis, our gender gap hypothesis, is supported. But the null hypothesis would say not so fast. The null hypothesis says, look, the overall distribution of cases over here in the total column, this is called the marginal distribution of the dependent variable. Overall, 40.4% of the entire sample said diplomacy, 25.6% of the sample took the middle position, and 33.9% of the sample said force over diplomacy. So the null hypothesis focuses on this marginal distribution of the dependent variable and says this. It says, well, if 40.4% of the total sample favor diplomacy, that means that any way you divide up this sample, by gender, by race, by income, by education, 40.4% of whatever category you're looking at will favor diplomacy over force. So for example, the null hypothesis says you can expect to find 40.4% of these 530 females to favor diplomacy. You would expect 25.6% of these females to be in the middle position, and you would expect 33.9% of these females to be in the force category. Any departures from those expectations, as we've seen here, are explained. Any departures are explained by random sampling error when the sample was taken. So the null hypothesis, the first thing about chi-square is you replicate these percentages down each of these columns and then compare what we observe with what the null hypothesis expects us to have found. H sub 0 is based on the expectation. So again, we're expecting the null hypothesis to be true. We're according it that respect. H0 is based on the expectation that the distribution of cases down the female column and the distribution down the male column will be the same as the distribution down the total column. So 40.4% of females and 40.4% of males will say diplomacy, 25.6% will take the middle position of both genders, and 33.9% of both genders will say force. Any observed departures from this expected pattern are accounted for by random sampling error. So that's the setup. We have to determine first what the null's model of the world, what would the data look like if the null hypothesis were correct, and just how far does our observed data depart from that expectation. Now, here's the calculation, and I know it looks a little intimidating, and indeed it is tedious. But let's work through it because you'll get a real intuitive feel here for the chi-square test statistic. There's chi-square, capital Chi, Greek letter, squared. It says to do this. For each cell in the table, take the observed frequency of cases, that's F sub O, the observed frequency of cases, subtract the expected frequency of cases, and we'll look at how to derive the F sub E here. These are the expectations under the assumption the null hypothesis is correct. Subtract FE from FO, square that amount, square that value, and then divide it by the expected frequency for each cell. Each cell then has a value, a number in it, that summarizes departures or concordance with the null hypothesis expectations. I've just got the steps here. So for example, take an example here. Find the expected frequency for each cell. For example, since 0.339 of the total sample fall into the force category, the dependent variable, the expected frequency for the female force cell would be 0.339 times 530, or about 180. We'll come back to that slide. Here are all the calculations for the entire crosstab. Here's the female force cell here. Here's the 160 females that actually were observed to have fallen in this cell. Here's the expected frequency. Where did this come from? We multiplied 0.339, since that's the proportion or the percentage for the entire sample, times the number of females, and we came out with about 180, 179.7. But I just want you to get an intuitive feel here for where these come from. So for example, getting back to our example, we observed 160 females. We expected based on the null hypothesis about 180. If you subtract 180 or 179.7 from 160, that's the next part of the formula, you get about minus 20, minus 19.7. If you square that, you get 388. And then if you divide the 388 by the expected frequency, which is 179.7, you get a value of 2.2. So for this cell, the null hypothesis was off by 2.2. Is the sort of the resolution for that cell. The null hypothesis said, well, you should have gotten 0 here. You got 2.2, but you got 2.2 because your departures from expectations occurred by chance. Notice the calculation for every cell. If you go back to the formula, the overall statistic for the table is determined by summing up all those cell-by-cell calculations. All right, now we add all those cell-by-cell calculations up. We add them up and we get a value, an aggregated summed value of 15.2 for all those numbers. So what?